Welcome everyone. This is either the second or third seminar talk on in context learning, depending on whether you count the one that was some months ago. So I'm going to begin by briefly recalling what we did last time, just to set the stage for the discussion today. And this is all speculative in some sense, right? So this is meant to be a stimulus for investigation. Okay, so you can see here, maybe here rather, the key hypothesis from last time, which was this question 2, and it is the hypothesis which, following on from one of the comments last time, I'm going to call the contexts as what context 2 weights hypothesis, just for the sake of having a more useful term of reference than question 2. So contexts 2 weights. And this was the hypothesis that given a transformer for some kinds of distributions of tokens, if you prepend a context, in this case x underline, the behavior of the transformer in prediction on that task is in some sense similar to a transformer with a different set of weights. The context is x underline xl plus 1, so that whole sequence, and the next thing you're trying to predict. You're trying to make a prediction based on what comes after that, that's the blank. And the hypothesis is that with that context underlined in green, the behavior of that transformer is similar to a different transformer, that is parameterized by a different weight vector w prime, on just that new input data. Alright, now that's probably not true for all distributions. It's probably not true at the beginning of training for a transformer, etc. So this has to be rather carefully understood, and maybe even very carefully understood is false. But we're going to explore this hypothesis and what it might mean for the structure of phases and phase transitions for a transformer model in today's talk. Let me see if there's anything else I want to say from these boards before I begin. Yeah, so the second half of the last talk was me arguing in a pretty rough, not very serious way for some evidence for this question 2, or at least how it might arise. You can do better than what I did last time, using ideas like singular value decomposition and some RG flow ideas, but that's a project for Ben and Zhongtian to tell you about at some future date. I will pass off that problem. So that's not meant to be a full justification of question 2, it's a question whether or not that is valid, but we're going to assume it for now. Any questions about this part before we move on? Okay, so I'm going to start today by formally putting the transformer, and more specifically the transformer plus the data distribution you see in, say, the GPT paper, so you could say the large language model perhaps, which is this combination. Put this formally in the context of SLT. So if you'll follow me, we're going to move to a fresh set of boards over yonder. So let's go for a walk. Alright. So, I need to say formally what the data distribution is for this class of models. So given some maximum context size C, so that's around 4,000 tokens for the model you'll find called GPT 3.5 on OpenAI's service, for example. So the way we generate data is we sample consecutive tokens sequences of length C from a corpus, e.g. of text, if it's a language model. So let's call those tokens T1 through TC. Then we form the pairs which is the first token, comma the second, so this is the input and this is the output in each of these pairs. The second sample, well, the second thing in the true distribution is the sequence T1, T2, followed by the next token T3, and so on. Alright, so that's how you generate samples from the true distribution. Note that sequences in this true distribution, sequences of all lengths are equally likely, right? So it's not that there are more short samples in the sense that the length of the input is short. There are not more short samples than long samples. The reason to spell this out is this isn't, I guess, as far as I can tell, detailed in the Huang-Hada paper, which is what we're basing the formal discussion of transformers off, and we haven't covered it in the earlier seminars either. And it's crucial for actually formulating this pair consisting of the transformer model and the true distribution as a learning machine in the language of SLT. So if S is the set of possible tokens, which if I remember correctly is on the order of 40,000, I think, for say GPT-3. We actually have true distributions, and I'll denote them with subscripts. So there's Q1 XY, that's on pairs, right? So that's something like this. We have Q2 XY on S squared cross S, and so on. Okay, so note we make predictions in the notation I used last time. So TW means the transformer with attention weights W, and again I'm ignoring the rest of the weights in a transformer model. We make predictions for samples that look like that, and predictions for samples that look like that, all using the same weight vector. So this is a little unusual, right? Where so in SLT we would typically call this X, right? The space on which the true distribution is a distribution. So even though we're really considering somehow a family of true distributions over different context lengths, maybe context is the wrong word, input lengths, we're making predictions using the same weights. Okay. Now, as defined in, say, the Fong-Hutter paper, the loss associated to a given weight vector W is the sum over the losses that are obtained for each one of these lengths. I probably wrote this slightly differently last time, so maybe I'll spell out what the ingredients here are. Okay, so the first board defines an effective distribution over the disjoint union. Maybe I'll write this somewhere. So the actual space X over which the true distribution lives is the, I could write it like this, the disjoint union over L equals 1 to C minus 1 of S to the L, Cartesian product with S, and the true distribution lives on that and is given by all these things on the disjuncts. So, alright, so the first board defines effectively all these distributions, and then the loss function is the average over that true distribution of the cross entropies, where this here is just a has all its probability mass in the true next token. Oh, sorry, it's given by that distribution over next tokens given the t underlines you see in the data. And empirically, so if you take a sample, the empirical approximation to that loss function is, I think, what I put up on the board last time. All right. So the learning machine WP Q var is specified once we give, I've told you the true distribution, I've told you X, W is the space of attention weights, and I don't care about the prior for now. So once I have to give you the model, and the model just is the transformer. So as usual, we assume that the distribution over inputs X is not modeled, so that just factors off. And this part here is just run the input sequence through the transformer, read off the t''th entry of the output of the softmax. That's the probability of that token given that input and that weight vector. So that's it. All right, so that's the formulation of the transformer plus this form of data distribution as a statistical model. Next, I'll compute quickly the KL divergence for you and show you that up to the usual entropy term, it's the same as this loss function, and then we'll start talking about the posterior. Are there any questions? Okay. So I'll be a little bit quick with this because it's a calculation that many of us have done numerous times, but I do want to at least quickly go through why, once you have a learning machine, you can formulate the KL divergence between the true distribution and the model, and why that reduces to this loss function, whose empirical approximation we've discussed last time as being the loss function, the loss you would associate to a sample in the usual machine learning sense. All right, so the KL divergence given parameters W is by definition the integral over this space of, well, this space X. And maybe one reason to do this is that it's quite common when you're looking at SLT for the first time to be a bit confused by the fact that in, say, the grey book, you'll see things like px given w. You won't usually see things like conditional distributions like we're dealing with usually when we're modeling neural networks. So there's this little wrinkle here. Okay, so that's the KL divergence by definition. We can do a couple of things, so we can rewrite this as t prime given t times qt. We can do the same with the numerator and denominator inside the logarithm, which replaces this by this. And by the hypothesis I mentioned before that we're not modeling the distribution over x, it gives us this. So we get a cancellation. Now we observe that X is a disjoint union over spaces, so I can write this as a sum. So the main point I want to make here is that it's interesting to think about the interaction between these different summands. Right? The loss is, or the KL divergence is made up of contributions from each of the input lengths. And obviously the phenomena of in-context learning, or this contexts as context to weights hypothesis, relates these KL divergences or loss functions for different input lengths. And this is one of the ways in which thinking about a large language model, and I'll use that term henceforth to refer to the combination of a transformer and a data distribution of this kind, which mixes inputs of different lengths but uses the same set of weights to compute predictions for all of them. So a large language model from the point of view of statistical learning theory is interesting for several reasons, and one of them is this phenomena, mixing different lengths and the interaction between the KL divergences for those lengths. All right, so we get a sum like that, and I'm going to term that summand KL. That will be less confusing in the notation than it is to say out loud. K superscript L meaning the KL divergence for, that's kind of like a, don't know if I want to call it a submodel exactly, but for the model. So that's the KL divergence for the model with the same set of weights, but the model and true distribution being restricted to sequences of length L. All right, well, that's a KL divergence, so you can just split that logarithm into a difference, and you'll see that that is an entropy term, the entropy of the true distribution, or it's negative. Plus what I wrote earlier. Right, what's left is just the cross entropy. Okay, so in particular, minimizing this this KL divergence means minimizing this loss. Okay, so now I'm going to talk about the Bayesian posterior associated to this model. So let me just recall the definition. So given a set of samples, now what your mind should be going to is the fact that, well, if you sample from this distribution, you'll get a distribution over the input lengths as well, right? So you could kind of divide any sample into some samples of each length. So that means there's a natural decomposition of the posterior as a product of contributions from each of those lengths. All right, so given a set of samples of varying lengths, posterior is, by Bayes' rule, and over the partition function, the prior, and then this here, where LNW is the empirical loss, which is exactly the loss you would write down, the thing you would take a gradient step against for the transformer given a sample by the procedure that I defined earlier. So the empirical loss is the cross entropy. Yeah, I actually wrote this incorrectly in the notes. The second formula is correct. So if we just look at the earlier formula for L, if I get a sample, then that's some particular T underlines, and given a T underline, I'll get some precise next token, and so the what I'll get instead of that cross entropy is exactly negative the logarithm of the output of the transformer. Okay, so let me briefly recall how model selection is supposed to work in the context of Bayesian learning. So the model evidence, which is this denominator,
Has it moved across, sorry?
Oh, thank you, yeah. So we view model selection, I don't know, I'm not here to convince you that this is the correct way to choose a model, but anyway, the dogma is that we view model selection as being about selecting models with higher evidence. If you accept that view, then it makes sense in the context of very large models like a transformer, perhaps, to view model selection as internalized. So rather than selecting between different models, we're really selecting between given regions of parameter space, which we integrate over and compare the evidence for. And that's the point of view that's emphasized if we talk about phases and phase transitions in a learning machine. So we view model selection as being internalized. There's a single model So you might call it phase selection. Where two regions, W2, W1, are preferred according to their evidence. Maybe this is a misuse of the term, but so for a in 1, 2, you can compute this integral. See which is larger, or what is the same, you can take the negative logarithm and see which is smaller. And that's the free energy, of course. And one way to think about the free energy is it's the effective Boltzmann weight for a coarse-grained version of the distribution, where you partition W and integrate the posterior over each cell of the partition. Okay, so I'm just setting up the general story of so a phase is going to be some region of weight space satisfying some conditions, which we won't talk about here. When we say model selection, what we're referring to ultimately is where the posterior concentrates for a given value of n. Right? As you increase n, the posterior will shift around. It will prefer certain regions of weight space to others. Those preferences, when they jump, those are called phase transitions. So what I'm leading up to is a discussion of how these peculiarities of a large language model, meaning the peculiarities of the transformer model itself and the nature of the data distribution, how these feed into special features of the posterior and the free energy, which are not generic, which are somehow special to large language models and perhaps related in an interesting way to this hypothesis, question 2, or the contexts to weights hypothesis. Maybe I'll pause for questions. Are there any questions about this foundational stuff? All right, then I will proceed.
Hi, Dan?
Yeah.
Can you hear me?
I can.
Hi. I had a question about the data sample dn.
Yep.
In this case. So I could imagine a situation where for different lengths L, small l, you have different amounts of samples. If that makes sense. I'm not sure exactly what you assume here, but I could imagine there's some complicated combinatorics.
The way that the
make
transformer
sense?
is usually trained, you have equally many samples of each length because you first sample a context and then you generate a sub-sample, I guess, of each length. Yeah.
Okay. All right. So it's equal amount. Thank you.
I think, however, as I'll discuss a bit later, that effectively, if the hypothesis about contexts and question 2 is correct, that it's not always the case that you're really sort of equally training on all lengths. And that's consistent with a kind of naive view of training a transformer or any model, is that it will tend to go for the low-hanging fruit first. So it's probably easier to train next token prediction given one previous token, just looking for sort of naive correlations, than it is to do some more complicated thing with many tokens in the context. So maybe it's reasonable to have an intuition that even if the data sample contains things of all lengths, that like at various stages in training, maybe shorter things are making more contribution to the gradient or something. I'm not sure. But,
yeah, I mean your entropy rate, your effective entropy rate that you'll see will also go down the larger your context window is. I mean, this would vary as well, right?
I'm not sure what you mean by effective entropy rate.
If I only see like 3 previous tokens, there's like a limit to how much I can predict about the next token.
Oh, I see.
If I increase the token length, then and that itself, like that's a objective fact about reality that will vary. Yeah.
Yeah, that would be. Yeah, that's interesting. Okay, so part of what I want to do with this seminar is illustrate how some of the kind of basic fundamental theorems in SLT can be used to reason about things. It won't always be completely rigorously justified, and here's an example. So one of the key identities that you can use to think about what's happening in a singular model is what we've termed the free energy formula. It's developed in Watanabe's, not so much in the grey book, the way we're terming it, because that's assuming the realizable case, but in the WBIC paper and in the green book, in circumstances, for example, the renormalizable case, you have the following formula. I'm going to apply it a bit outside where we know it's justified, so this is dependent on like ongoing research, but it's at the level, I think, of like reasonable physics talk. So the free energy formula says the following. It says that, and here there's another typo in my notes, I apologize. It says that if you take one of these regions and they satisfy some hypotheses, which are a little technical, and those hypotheses sort of include there being a point in this space, this subspace of parameters, where which is an optimal parameter, so it minimizes among all the parameters in this set this function ln, and then there's some further conditions. It says that the free energy that I just defined is approximately, so asymptotically in n, given by n ln wa star plus lambda a log n, where this is to do with the singularities of, well, let's say k minus kwa star. Right, so this is not assuming that this is a point of w0. So I'm not assuming this is 0. This is not the 0 level set. And these are not the singularities of w0, the 0 level set. These are singularities of some other level set. And lambda a is a measure of the complexity of those singularities. Okay, so this is a very important formula. So roughly speaking, this is familiar. It's an energy term plus an entropy term. Okay, so I'm going to take this for granted in the following discussion. Okay, so we take a sample. It's got in it sequences of all different lengths, and each of those points in the sample contributes to the free energy of any phase, any region of parameter space. So let me just write out what the free energy is, or what the partition function is.
Sorry, Dan. When you say singularities of k minus k of w star,
yep.
What's the input for k? Is it just arbitrary w?
Yeah, w in this set, wa. That's right. So wa is a subset of the space of parameters w. That's kind of sitting inside w. And by this function here, what I mean is the function that sends a weight that shifts the origin of the output.
Gotcha, thank you.
Yeah. So it will be 0 at wa star. Now, over all of w, that function may be negative, right? Because it's certainly, if we're imagining a phase which doesn't correspond to a region near W0, then it's certainly true that there are other weights W that make that difference negative, because K there is less than K at this particular point. But on this WA, this function should be non-negative. So that's what I kind of said earlier, right? That WA star should be a local minimum of the energy.
Cool, thanks.
Yep. All right, so let's just write out in the formula for the evidence on the previous board, there was this ln there, and we have a formula for ln in terms of the outputs of the transformer. So let me just substitute that in. That we get ZNWA, whoops. That's the integral. So the product over all the tuples in the sample, I run the transformer on the input, and then I take that position in the output. Okay. So, well, now I'm going to think about what happens if the context to weights hypothesis is true. Okay, I'm just realizing that I've forgotten to feed the cow, and if I don't feed the cow, you're going to hear moos behind me every 30 seconds soon. So please excuse me for 2 minutes while I go and throw some hay to the cow. Alright, I'm back. Bet you've never seen a seminar interrupted for that reason before. Okay, so let's continue with this, assuming this hypothesis is true. So suppose the context to weights hypothesis is true for some sample dn. Now I'm going to later on invite you to consider any given sample. If you think about a real transformer, it's sampling text from all over the place. Some parts of the sample will come from some sort of subdistribution corresponding to a certain task, for which we might imagine that there's a context or a set of contexts that make this context to weights hypothesis true. Approximately true. It's very unlikely to be true for a whole sample dn, but just keep in mind some, just restrict to some subsample for which it's true, for example. So that's how we're going to proceed. Okay, and we're going to suppose that each one of these inputs looks like some context, see underline, a sequence of tokens that identifies the task, and then the actual input. And to say it's true is to say that if I compute the output of the transformer on that and look at the entry for the true token, that it's approximately maybe I'll write it out more carefully. So in the following sense. So I'm going to assume an even stronger statement, which is that it's not only true for the weight W, but for all nearby weights and in some coherent fashion. Okay, so we suppose for all W in WA, there is a weight depending on the context C and the weight W, such that first of all what I wrote earlier works. So the effect of prepending this context C is to perform a computation as though you're a transformer at this modified weight on the input stripped of the context. And further, I want to assume that this varies somewhat reasonably, let me just say continuously, in W. Okay, so there's some mapping for all the points in the phase given this context. Right, so we have a picture that looks now like this. We have WA, we have WA star, and there's some other region of weight space, which is what you get when you look at the transformer on any of the weights in this phase. Okay, now why is this somewhat reasonable? Well, if the first line is true, then it's true in some neighborhood, perhaps, right? So you can restrict inside the phase and restrict given that approximation until you get something that looks a bit like this. And the kind of rough argument for why this might be true that I gave last time would suggest that this isn't, if that's true, then this is as reasonable. Okay, note, and this is what's interesting, or what's worth paying attention to here, is that the map FC is likely to be highly degenerate. As in it's many to one. Okay. Why? Well, just consider this in the kind of rough picture I was painting last time of the kind of mother singularity of the transformer as routing calculations to these different kind of context-dependent weights, which are these FC of WA stars. So you could imagine that this phase WA, it may be able to deal with multiple different contexts, right? So DN is sitting inside a larger distribution where you might see different kinds of tasks. So you might see C underline, you might see C underline prime, and if this is the right way to think about in-context learning, then you would have something like this context to weights hypothesis for a single WA and multiple different contexts, right? So that means there's much more information around WA than you would expect. I mean, this image thing, this FCWA star, under this intuition, just knows how to deal with this particular task, right? So there will be many directions. Another way of saying why it's degenerate is that there will be many directions in weight space going away from WA star which have to do with other problems that have no relevance to C underline and its particular task. And you would not expect those directions to change FC underline, right? Because they're irrelevant. So there will be many directions in which the derivatives of FC underline are zero. So that's the statement of degeneracy. All right, so now let me do a little calculation with the evidence. Alright, so that's the definition. I'm assuming that they all start with this context. Ah, sorry. I think that was an X before, right? Yep. Alright, well, the hypothesis says that I can replace that by the transformer somewhere else. So now's the interesting part. Okay, so if you look at that last line, it looks kind of like the partition function you would define for integrating over this region here, right? Because if you were to compute the free energy, define the partition, the model evidence for this region, you would integrate dW, phi w, you would take the product over the data samples, t of the weight that lives inside that region, etc., etc. So if FCW were a bijection and its Jacobian was something simple, then this basically would be the evidence for that region. But I'm arguing that FC should be thought of as highly degenerate, so it's not that straightforward. So what I can think about here is that for every point, so if every point here, there's some pre-image, right? So I can think about integrating over this region. So the usual change of variables formula would tell you that you would get something that looks like this. So W is now arranging over here, so it's like this point. But to do this integral, you also need to integrate over the fibers, roughly speaking. I mean, this doesn't always work, of course. You can't always do integrals like this, but if these fibers were regular, this would be fine. Maybe they're not, so it's more complicated. But for today's discussion, I think the intuition is fine. Right, so there needs to be some factor here, which basically corresponds to integrating this measure over the fiber. And I'm just going to call this phi bar. So I'm going to absorb that in here. I don't need to do anything with it. Okay, so this kind of looks like the evidence for that region, as I said, but I've changed this multiplicative factor from phi to phi bar. Now, if this were regular, it wouldn't contribute to the asymptotics for the same reason that the prior, as long as it's positive at the singularity that controls the asymptotics, it doesn't contribute to the asymptotics in the usual situation we're dealing with in SLT. But this FC is likely to be zero, or to have singularities that contribute to this integral. So the argument I'm about to make is that this will be less than what I would get by just integrating the posterior over this region, sort of on its own. So where I take this data set. Yeah, the data set changed as well, right? So here I'm taking the thing that has the context in it. Here the data set that I'm considering with respect to the posterior that I'm integrating doesn't have the context in it. It's just this thing. Okay, so this is kind of this is the few shot data set, and this is the zero shot data set. Okay, so let me come back to arguing for this briefly. This is a bit hard to argue for unless you're familiar with how these integrals actually work, but what happens when you do these integrals is that you'll get contributions. So you'll get contributions from the factors that are most degenerate, and if, as I said, the prior is positive, it won't contribute, but if this FC map has degeneracies, they will sort of contribute to how degenerate the thing you were integrating originally was, which was the empirical KL divergence, or the LN, for this zero-shot data set in this region FCWA. So phi bar can only make that worse, and will make it worse if it's degenerate at this most important point, FC, well, assuming FCWA star is the most important point. Okay, this is a bit beyond the scope of this seminar, but by looking at how that asymptotics will work, it's somehow reasonable to think that you'll get the degeneracy you see in that integral without the phi bar, plus some extra contributions from the difference between phi and phi bar, which will make it bigger. Okay. Sorry. The more singular it is, those will contribute to the k factors that are in the denominator. All right, so that'll make it that'll make this smaller, so we get a less than or equals to. All right, so let me now sort of try and say what that means and why that might be interesting. Okay, the idea here. So let me apply the free energy formula to the left-hand side and the right-hand side. And by construction, they both have the same energy term. This is not a proof, but it's some idea that the RLCT that controls the free energy near W alpha star is strictly less than the RLCT that controls the level set that passes through FCWA star. And you think of that as being, because that's a more complicated singularity, right? So the idea here is this is a way of maybe getting rigorously, given more work, at the idea that this routing singularity that can send queries or direct predictions to these regions of weight space that are specially suited for a given subdistribution or context, that has to be more complicated. And the difference in the complexities is something to do with the degeneracy of this routing map, this FC underline. So the difference, and this, if you look in Xiaowei-Lin's thesis, I mean, this is basically to do with composing maps and seeing what the singularities do when you compose maps. So it's like a functorial story around the RLCT. Xiaowei-Lin's thesis has a little bit about this, so this is somewhat reasonable. Okay, it's a measure of the degeneracy of this map. Okay, here the intuition is that WA star is a more complex singularity. Then you need to be a bit careful because the functions of which their singularities are different, right? The one is the few shot data set and the other is the zero shot data set. Okay, now you don't have to believe the details here to sort of believe the general picture, which is that if it's true, the idea that contexts get mapped to weights, then something like this is the case, right? I mean, if the Bayesian picture is valid, then you're doing integrals over weight space, and there's good reason to think that if it's true for one parameter, the context to weights idea, then it's true for some nearby parameters. So you will get effects like this that say that the free energy for a given phase for which the context to weights hypothesis holds, that is, it directs predictions to some other regions, to some other singularities, the free energy of that can be thought of as having contributions from the free energy of these sort of submodels, these other regions, and the degeneracy of the maps that send you from one to the other. So that's the high-level point, and that, I think, is pretty solid. Of course, there's plenty of cheating going on here in the argument, but the general picture seems very likely to be true. Okay, how am I going for time? Are there any questions? I'll pause here. There's a little bit more to say, but
so maybe in physics we introduce fake degrees of freedom all the time. We have these ideas like the Hubbard-Stratonovich transformation, or even something like Hamiltonian MC, where you introduce a momentum. Like, if we can't define the transformation on the weights, the original weights themselves, can we somehow recover it by introducing fake weights, extending the weight space that we're looking over?
Yeah, that's a very interesting question. So it's pretty natural to introduce kind of it's a good question. I haven't thought about in this particular example how that would work. I mean, something I've played with a little bit is introducing kind of fermionic degrees of freedom. I mean, there's a way in which you do some of these kinds of integrals in physics by introducing sort of chain complexes, by introducing fermionic degrees of freedom. So I thought a little bit about what you're suggesting in that direction, but not here. I don't know why. Could you explain a bit the intuition for why introducing these additional degrees of freedom would make it more true, this hypothesis?
Well, the way that the previous tokens interact with the new tokens is through this nonlinear activation. It seems difficult to get an exact statement about how to transform attention into a weight transformation. But if you can insert the weights somewhere else in the attention, maybe it gets easier.
Yeah, interesting idea. Yeah, I'll have to think about that, but thank you. Any other questions or suggestions? Okay, so I probably have about 10 more minutes prepared, and then we can just have discussion as we did last time. So I wanted let's see. So I wanted to indicate one way in which this degeneracy, I mean the simplest form of this degeneracy, and elaborate on what happens in that situation, and informed by that speculate about what this means for the phase structure of a large language model, which is kind of where this is all trying to go, right? So unfortunately we've kind of used up these boards, so if you'll bear with me, we're going to move again to another set of boards, which is down in the caves, so please follow me. Don't fall in that hole. like if you can hear me but don't want to walk, that's fine. If you just reset your character, you'll get teleported down here. So that's the easy way to get to where we are now. Alright, so I'm going to suppose that we're given, so the previous discussion was assuming that my data distribution was just all in one context, right? Let me now assume that there's two. So my data sample consists of sequences with one prefix and then sequences with a different prefix. So now suppose, to illustrate the possible kinds of degeneracy in FC, that there are context C1 and C2, and our data set dn looks like some things in one and some things in another. So n1 plus n2 is n. And that the context of weights hypothesis is true for both of them. All right, and then let me do this integral again. Same integral. Well, I'll just get one factor, which is a product over the things that use the first context, and then another product over the second class of things. Okay. So I'll have a funny situation where this integral looks like it's integrating over two different parts of the weight space. Right, so in the first case, I'll get FC1 of W. So assuming context to weights for both. So approximately. And the other factor looks like it's talking about some other region. Okay, so the simplest kind of degeneracy we could imagine in these two maps is that they only depend on disjoint sets of the weight variables in some neighborhood of W alpha star. Okay, so here's W A, here's W, I said alpha, W A star. Let's just consider some coordinates u and some other coordinates v in some coordinate patch around WA star, and assume that, okay, so again, to roughly justify why this is somewhat reasonable, what are these weights? Well, they're attention weights, so they're query, key, and value weights, right? And the way I presented it last time, there was like frozen entities and unfrozen entities. And the frozen entities were the things that were contributing to this FC map, right? The nature of these frozen entities. So suppose that for these two different kinds of tasks, the transformer has learned to use different entities to process that information, right? because there's an entity for cars and there's an entity for colors, and they're different. So the weights that are involved in one of the specializations, FC1, is just different to the set of weights that are involved in FC2. And in general, that's almost certainly not true, but okay. So for the sake of illustrating the principles involved, I think it's reasonable enough. Okay, so we're going to assume that there are local coordinates. Is that there are local coordinates U and V near WA star such that I'm going to write it in a somewhat inaccurate way. I'll write it like this. What I mean by this is that the partial derivatives in all the v directions of FC1 are 0, right? The value of FC1 nearby WA star depends only on the u directions. And similarly, FC2 depends only on the v directions. Alright, well, that's a situation we understand how to deal with in terms of these asymptotics. It's covered in, I think it's remark 7.2 of the Grey Book. So that means this integral splits up into a product. That's the point. So this is WA. Well, I'm assuming the prior splits in as well, but the prior doesn't really matter for my purposes, so that's fine. So that's a product of, so FC1, it's of UV, because W has somehow become UV here, but FC1 of UV only depends on U, so I have stuff that only depends on U, and I've got a factor here that only depends on V. Alright, so this integral is really just don't quite know what to write here for the integration domain. Doesn't really matter. Hopefully you get the idea. So it's that integral times this integral. Now what happens if you have KL divergences which are a sum, and the summands depend on different directions in the space of parameters, then the RLCT adds. Right, so I won't go through how that works, but what this will look like is it will, when we go to the free energy, mean that we have a free energy formula that looks like, well, what's happening at WA star. Now this has contributions, this term here, if you think about it, has some of the summands there look like things around FC1 of WA star, and some of them come from FC2 of WA star. And then you'll just have two contributions to the RLCT, one that comes from the singularity at FC1 of WA star, and one that comes from the other place. Right? So there's like WA star, and then there's these two kind of daughter singularities. And something's happening near here, and that controls the asymptotics of the integral that's going on around here. So the point I want you to take away from this example is the general idea that you might understand the phases and phase transitions of the mother singularity, so the whole training process for the transformer, under these hypotheses. So first of all, there's a backstory to how you understand phases and phase transitions into a first approximation that comes down to the free energy formula and a change in the balance between the energy and the entropy terms. So the free energy formula is what controls phases and phase transitions, and what I've sketched here is an argument for how you can try and understand those phases and phase transitions in terms of contributions from each of these daughter singularities. So the kind of idea would be to go and look for some description of the overall phase transition system of phase transitions in terms of the following ingredients. This is where I'll finish. So it's a divide and conquer idea, right? So the idea is that these daughter singularities are simpler, their phase structure is easier to understand, and the complexity is from these many, many hundreds of daughter singularities somehow having superpositions of their phase structure all together to form the behavior of the overall model. Of the full model in terms of A. Well, the acquisition of a given context as an active thing would be almost certainly an example of a phase transition. So there's a phase transition, you would suppose, where a given subdistribution picks up a context and the model understands what to do with it. So where a given context is recognized.
Could you move the order? Okay.
Oh, thank you, yes. Is recognized, i.e. the context to weights hypothesis begins to hold. So at the beginning of training, this hypothesis is not going to be true, right? If it's ever true. But at some point, maybe it begins to be true for some subdistributions, and maybe not all at once. So the point in training, or the point at the size of the sample, where it becomes true for a given subdistribution, would be this kind of phase transition, type A. Begins to be valid. And then B, you'd have phase transitions in these, I'll just call them submodels. I don't really know. They share the same parameter space and potentially the same number of dimensions, right? So it's maybe a little hard to say that they're submodels, strictly speaking, but so I don't know the right term. But that would be, so as on the previous board, that line on the bottom, the first term, the energy term, has some contribution from each of those daughter singularities, and the RLCT term also does. So the free energy kind of adds in this simple circumstance where it splits completely. It just adds. In general, it won't add. There'll be some interference. But you can see how from that description, the free energies and therefore the phase structure kind of merges across these daughter singularities. And if you fix all the daughter singularities but one, and that undergoes a phase transition, well, that will cause probably a phase transition in the overall thing. So that's the kind of phase transition that I'm talking about in B. And then there would be interactions between phase transitions of type B. And this picture has a kind of interpretation in terms of deformation of singularities, in which this kind of interaction between different deformation parameters is not unusual. Okay, so maybe I'll just briefly summarize. So this is an exploration of what would be true if this idea of in-context learning being a kind of discovery of a different set of weights for a transformer, if that were true. If that were true, there would be kind of unavoidably some consequences for the nature of the posterior and the free energy along the lines of what I've sketched. So I think the real question here is whether or not question 2 is true. So yeah, it seems like a very interesting question to think about. I'll stop there and take questions. Thank you, everybody. Who's first? Yeah, I guess Matt was suggesting last time to look for the simplest model in which you could try and discover whether this hypothesis is true. That seems quite important. It also, I mean, there's, for an algebraic geometer, one is always tempted to go to the relative case, right? So RLCTs, or birational invariants, just of the variety itself of true parameters. As soon as you see that, you wonder about maps, right? So it's also quite natural to try and interpret in context learning in terms of maps from parameters to parameters. Geometrically, that's kind of sensible.
Like how in that paper, YC and GPT learning context, how they think of this like entity vector updating as like a dual form of what they call, like, I guess, linear attention, but basically you mean like just defining a function that takes the entity update method to the gradient descent method.
Right. Yeah. Hopefully we can figure out a version of that. Just for some background, I guess we promised 2 seminars in a row to present those papers. It's kind of we first have to find a version of those papers that we would feel what is worth our time to present. So we're still doing that. That'll come at some point. But yeah, there probably is some link for some data distributions between in-context learning and gradient descent. But I think we want to present it quite differently to the way they're doing it.
This is maybe just a much broader question, but how do you think this links to, I guess, more mechanistic interpretability approaches? Or, we're trying to read the thinking of a neural network. You have like this logit lens stuff. How do we start laying the link between this kind of picture and that?
Yeah, it's a good question that I don't really know. I guess maybe we have some intuition for the role of attention in directing computations to different entities, right? I think many people have seen phenomena like that in NLP and other kinds of transformer tasks. So I guess my first not very well thought through reaction to that question is it suggests that you can decompose interpretability into 2 parts. So one is sort of understanding the routing, and the second is understanding how to deal with each subtask. But that's probably, I don't think you would need this picture to have that insight, right? That seems like a pretty natural thing to try and do anyway. I think maybe so one of the things I'm really interested to look at more closely in some of the more recent work coming out of Anthropic and probably elsewhere is the link between phase transitions, or something that looks like phase transitions in various measures of effective dimensionality, and the acquisition of kind of structures in the network, right? And maybe you can match up the phase structure there with some picture that looks like what I'm presenting here. It's going to be very difficult to argue the theory is sort of it's going to be very hard to touch base with any concrete particular networks or representations, right? But maybe there's at the level of those phase diagrams, there might be actually, like at that level, a connection between some theoretical picture like this and the more mechanistic interpretability picture. So it would be, of course, very suggestive if you're studying mechanistic interpretability and you see the order in which certain kind of structures are learned and appear, and some sort of, the generalized susceptibilities which appear to diverge, like the rate of change of the effective dimension in this toy models of superposition paper. If you saw some sort of structure in those generalized susceptibilities, and in the theory you could also see that these sorts of things should arise in the training process, then maybe you could point to measurements of those generalized susceptibilities, and even if you can't figure out what's going on inside the network, conjecture that something has been acquired, right? So you could, even without an ability to say exactly what it was that it was acquired, you might be able to recognize a signature of the acquisition of, for example, in the context of today's talk, acquiring this map that sends a sequence of tokens in context to some other transformer. That phase transition, the type A phase transition, maybe there's some signature of that you can detect, and you may not know what has been picked up, but you can then go looking for it, right? So maybe that's a way in which these two pictures could mutually reinforce each other.
I kind of a question based on Matt's suggestion last week about finding the smallest model that can perform in context learning. Do you expect it to be something as like nice as like a one-layer 10H network, or would it have to be like a much bigger model? Or I guess we could just like check, right, with like a single layer attention transformer.
It could be very universal. I don't know. I mean, what supports the ability of the transformer to compute on arbitrarily many tokens? It's just that there's a sum, right? So in the softmax, there's a sum. That's it, right? So you can add as many things as you like to that. I mean, you have to reuse the weights in some way, right? So that's the other thing. So there's some sort of weight tying. But if you have both of those things, yeah, I don't know. I have no intuition for how simple it could be before you'd see something interesting. I guess, I don't think people have observed in context learning in simpler systems than transformers, but that may be just due to the fact that it's very difficult to train anything else on a sufficiently large data set to see it emerge. It's not that you'll get in context learning on arbitrary data sets, right? That's the other interesting thing that I don't know how to think about, and which I haven't touched on here. It's not enough just to have this. I mean, the way I presented it, something interesting about the data distribution was that you see sequences of different lengths, right? But that's not sufficient, probably. There's a paper out of DeepMind that sort of argues for you need some sort of long-tailed distributions in the truth in order to elicit in context learning. There's understanding the relationship between the kind of geometry induced by that kind of true distribution and the emergence of in-context learning would be also very interesting. Yeah. So I don't know whether we should just look, I guess.